everyone, and welcome back. This is TheHappieCat here, and today we're going to take a look at the A-star algorithm as a part of our series on pathfinding. So if you're just jumping in now, you may want to look back at previous videos where we looked at the breadth first search, depth first search, and then Dijkstra's algorithm, and today we're going to do A-star. So just to briefly review, so we have this is our environment. We have a little block going through a maze to a goal position that is now off screen. The environment is much larger now. We can move up, down, left, right, or any of the four diagonals. So we're adding diagonals now, but it doesn't make too much of a difference. The only thing is that we cannot move onto a gray square. You can think of those as walls. And then the red squares are slow spaces. So if you go on a red, you'll slow down. If you go on a dark red, you'll really slow down. So the bright red's cost is 3 to step on. The dark red's cost is 5. And then a white dot is 1. So just to briefly review, we had the breadth first search, which just found the shortest, the smallest number of squares to get to the end. So you can see every time it passes through a red spot is when it kind of stutters and slows down. So it's not really calculating, oh, should I take a detour that might actually be faster? It's just finding the least number of squares to the end, kind of a naive approach. And then just for giggles, the depth first search, same as the breadth first search logic-wise, we just use a stack to queue up nodes instead of a queue. So that looks like that, which is a bit of a mess. It's visually interesting. It's kind of cool, kind of interesting to look at, but this is obviously not the shortest path. But then we have Dijkstra's algorithm, which actually does take into account the cost of moving to these different colored squares. And so actually Dijkstra's algorithm, it explores the entire graph and finds the shortest path to every node pretty much by the end, but we're only interested in the path from the goal node to the start node. So Dijkstra's algorithm, this was something I kind of forgot to touch on. Technically, it searches every single node in the graph. I kind of erroneously had it just stop at the goal for the sake of explanation. I don't know, but if you burn it into your brain, Dijkstra's is supposed to explore the entire graph, find the shortest path so far to each node, and then once you get to the goal node, you'll still keep searching till every node has been calculated, and then you will return the absolute best, shortest path. Now let's look at A-star. So we'll first plug in Dijkstra's. We'll see it calculates this path, and I've calculated the times down here. Now, sometimes, this maybe isn't helping my case, sometimes the A-star in this case does better. I may also not really be optimizing it well. In this case, it does do better. You can see it's 1.32 seconds to do Dijkstra's. It was 1.289, so 1.29 seconds to do an A-star with the Euclidean heuristic. And I'll explain the difference between these different heuristics, Manhattan, Euclidean. There's all sorts of different ways you can kind of calculate the score that we use in A-star, but it's basically the same algorithm. So let's try Manhattan too. This is a different way of doing it. You can see Manhattan was actually worse than Dijkstra's. Yeah, Dijkstra's 1.32. Manhattan distance was like 1.35. So this is where the heuristic, we'll talk about it later if it makes no sense to you. There are different ways you can kind of calculate things in A-star that will be better depending on the type of problem that you're working on. So you can see the cube, it's unlike breadth first search, it's, you know, avoiding some of the red spots and taking detours where needed. We can quickly just show both of them on the same screen. So we have A-star, the Euclidean, and then we have this breadth first search, and you can see they've totally diverged to different paths, and the breadth first search is going quite slow. So that's just kind of an overview. I had to say breadth first search is the naive approach, depth first is no. Dijkstra's algorithm takes into account the costs but has to explore the entire graph, so it will perform likely worse than A-star, which is calculating the shortest path with using estimates so that we're not looking through the entire graph. So if I just had to summarize what is A star, it's finding the shortest path within a bounded region, not necessarily looking at the entire graph like Dijkstra's algorithm. So better performing, shortest path. And A star is also what is most commonly used in games in production. So I think it's good to know. Now, I'm assuming that you are familiar with Dijkstra's algorithm. You saw the previous video. If you're not, or if you felt like you were following along but you didn't totally get it, I recommend really reviewing that, looking up resources, writing out examples, because this is really similar to Dijkstra's, and it'll be a lot easier to understand as we go through it if you really understand what's happening with Dijkstra. So we'll give a high-level overview of some of the differences in A star, and then we'll walk through the code and see how it's working in practice. All right, now if you remember, in Dijkstra's algorithm, we would calculate the distance from the start node to some node x. So we'd calculate what is the shortest distance to some given node so far that we found so far. So distance from start to some node x. Now we can rename this as g of x. So you input x, you output the best distance so far from the start. Now A star also has another sort of function we're keeping track of, and this is what I'll call the heuristic score, the heuristic cost. So the heuristic score, and we could call this h of x. So you input some node x, you output some score that we're going to add to this value. So A star uses both g of x and h of x. Now what is a heuristic score? Why does it matter? If you remember, there were two buttons I used in the demo, one with the Manhattan distance, one with the Euclidean distance. Basically, this score is an estimate from node x to the goal. So g of x is our calculated distance, our best distance that we found so far from the start to our node, and then h of x is the distance from our node to the goal, and it's an estimate. So to give you just kind of an example of what I'm talking about, let's say this is our start, and we've explored through some graph like this. We've just gone all over the place, and then this is our node x. So this is the node we're checking, and we know, let's say all of these are like 1, 2, 1, 2, 1, so 3, 5, 7. So we know our g of x score for this is equal to 7. We know that for sure. That's our shortest, that's the shortest distance of the shortest path that we found so far to node x. And our goal is all the way down here somewhere. So this is our goal, but we haven't explored any of these nodes yet. We have no clue what's in there. We have no clue if there's walls or obstacles along the way. We have no clue how far it will actually take to get here. But we're going to use h of x. We're going to make some estimate of how far this line is. And that's where we can use different heuristics, or I guess just methods of finding this distance right here. And that's what can change depending on the problem. If you have some idea of how your maze or obstacles are structured, there might be different heuristics that will be more effective. And one thing, I'll add some links in the description to kind of for supplemental reading, for further reading on what makes a heuristic allowable in A star, what makes it effective. There are mathematical proofs proving that some heuristics just will never work for A star and some will. And we're going to look at two really common ones today. So you'll notice we had the Manhattan distance, and we have the Manhattan distance and the Euclidean distance. So the Manhattan distance is like, imagine you're a taxi cab in Manhattan. It's finding the shortest way given like that you have to turn street corners kind of like this. So it's pretty naive. It doesn't take into account these diagonals that we have in our board right now. So it's kind of naive, but the equation is just pretty simple. It's up here. So here's our Manhattan estimate, and it's the absolute value of the node's x position minus the goal's x position, absolute value, and then sum all of them together. So n.y minus goal.y plus n.z. And so this is also a good time to note that this will work for 3D or 2D games. In this case, we're in the XZ plane. That's just how it turned out. So Y will always be 0 for our case in our specific demo. But you could easily adapt this to 3D, or if you want to just keep it 100% 2D, you just don't have to calculate this Z value. And that's really all you have to do. And same thing for the algorithm, just change all these vector 3s to vector 2s of your vector 2 positions. So that's the Manhattan distance, and it's essentially looking like, okay, how many of these kind of square, like street corner turning moves do we have to make? And then we have Euclidean distance, which you've probably heard or you've done in like algebra class. It is like if you ever had a graph like this, like a Cartesian coordinate graph, not the ones we're talking about, and it's like, okay, here's a point and here's a point. Find the distance between the points. So that's what the Euclidean estimate is up there. It's the big square root and then the node's x value minus the goal's x value squared, and then same thing for all the others, and then square root that. So it's finding the distance between 2 points. And so if you remember our example from before, we're just saying, okay, we have node x, we're just going to estimate very naively, if we drew a straight line to the goal, how far away is that? And that's just to like bound the region more. If you remember, I was saying we kind of used this estimate to bound the region we're looking at, because let's say we have a graph of this size. This is our board, our game board. We're starting here. We want to go somewhere over here. You're probably going to want to look in this region, right? If you have a node over here, its distance to the goal is way more than this one. So it's like a decent estimate that you probably want to look around here, and this one might not be relevant to you. But that's where, if you have a really twisty turny board where there's a ton of obstacles, maybe this corner does end up being in your shortest path. You can't know for sure, and that's why it's a basic estimate. So to summarize, in Dijkstra's algorithm, we calculated the minimum g of x for every node in our graph. So that's the distance from the start node to any given node x, the shortest possible distance that you can go from the start to that node. And the only way we could be absolutely sure that that calculated distance was the minimum, we have to explore the entire graph. Now in A*, we do calculate this same distance, but we kind of reduce the amount of exploration we have to do by adding in this heuristic score, h of x. And so this is an estimate from x to the goal, but it's just an estimate. So I don't know, wiggly line, because we're not sure. My diagrams are really not academically sound, but I hope you guys can get the point. So we can call this sum of g of x and h of x as f of x. And we're trying to minimize f of x based on both of these calculations. We use this heuristic function to estimate which nodes are probably the best to keep looking at. Now the last thing I want to touch on before we start going through the code is the use of a data structure you may or may not be familiar with, which is the priority queue. Now I've updated Dijkstra's algorithm to use this data structure because I had some weird hacky thing to choose the next node with the least distance. If you remember, I literally wrote a comment like, this is a hacky link query. It was causing bugs, and I'm sorry for my vices of laziness. But this is not different between A* and Dijkstra's. This is something that is probably best to use for both algorithms, but it's new for our video series. So I thought I'd at least touch on what it is in case you're confused when you're looking at the code. We're going to go through the code. So if this is really small text, don't worry. But you'll see we use it down here. And so this is the structure we're using to choose our next node. You'll notice while the priority queue has stuff in it, that's how we're going to loop through. That's how we're choosing our next node to explore. And I'm not going to go really in depth about like why the runtime is better to use a priority queue or how it's really implemented. I'm happy to make a video on data, like different data structures like this if you guys want, but I'll just give you a brief overview in case you've never seen this before. So if you remember from the breadth first search, a queue is something where if we on-queue a thing, it's like lining up for the movie theater. This is the door. And, you know, we keep on queuing things. And if we day queue something, if we want to take something off and look at it, the first one that we put in the line is going to be the first one that comes out. So it's just like waiting in line for a movie, you know, assuming everyone's polite. Whereas a priority queue is not as like straightforward as that. It's more of in a binary tree structure. So let's just draw out an example. It's more of in a binary tree structure where, let's say, node A has g of x plus h of x. Let's say that equals, you know, 3. And so that's our current minimum. And let's say for B, that's 5, node C, 10, and so on. We're using this data structure to choose our next node through each iteration of the loop. So the node on top is the one that we think would be the most productive to look at because it has the shortest distance out of the unexplored nodes from the start, and it has the shortest estimated distance to the finish. So that's probably a good node to look at. That's basically what this means. And so then if we day queue A, because we want to go and calculate stuff with A, then these will shuffle such that, you know, they resort themselves by priority. So to summarize the basic new things from the last video, A star is really trying to minimize f of x, which is the distance, the shortest distance from the start, just like Dijkstra's, and some heuristic estimate to the goal. So we're trying to minimize this and not explore the entire graph by doing so. And the second thing is the use of a priority queue. So in the case of Dijkstra's algorithm, we would have g of x as a measure of priority. In our case with A star, we're going to use f of x as a measure of priority to know what's the next node that we should take a look at. What's most likely to be a productive thing to look at. That's how I view it. Now we'll go through the code, and once again, if you're familiar with Dijkstra's, you should get the gist of what's happening here, but I just wanted to point out a few key differences to be aware of. So first you'll notice our algorithm, it takes the start position, the goal, and then a string denoting which heuristic. And now the important thing with this is, like I said before, the A star algorithm is the exact same logic, no matter if you use a Manhattan distance or a Euclidean distance. This is totally encapsulated. So you can see whenever we try to calculate h of x, we call this function the heuristic cost estimate, and it just looks at what string did we pass in for what method we wanted to use. And I could keep adding, you know, I could keep adding cases, happy math, I don't know what that kind of heuristic would be, and we could just keep adding and keep everything encapsulated. So first we have our list of walkable valid nodes. These are anywhere that's not a barrier, so a white dot or a red square, just anywhere that we can actually walk on. And then we have our dictionaries for g of x and h of x. So g of x, the distances from the start, exact same as Dijkstra's, and then a dictionary for the heuristic score. Same thing where you input the vector 3 position of the node, so node at position 2, 0, 1, and then it'll spit out whatever score that was. And then for both of these, we're going to initialize them to the infinity value again. In this case, we're just saying the max value of an integer, but for the sake of diagrams, it's infinity. So an infinite h of x and an infinite g of x to start. And then same thing, we're going to say the distance from the start position to itself is 0, and the heuristic, the h of x for the start position, is going to be whatever heuristic we use. So just draw a straight line from the start to the goal. That's the start's heuristic cost. And then we have a set, I believe in the other algorithm, we said we kept track of unexplored nodes. In this case, we're keeping track of explored nodes. I'm trying to think if it does matter or not. I don't really think it matters. It's just doing things in kind of the flipped way. And then we have the priority queue, which will tell us what's the next best node to look at. So we start with the start position, and because the distance from the start to itself is 0, we'll just input its heuristic score. But really this is the heuristic score plus the distance from the start is what we're using as our metric for priority for all other nodes. And everything else has an infinite heuristic score, so this will be the first one off of the queue. And if it's the goal position, we'll stop. Once again, in Dijkstra's algorithm, we would actually remove this part. That was the catch I forgot to mention in the last video. And then we're going to add it to our explored set. So let's pretend we're starting at the start node. So we've added the start node to our explored set, and then we're going to get its neighbors. So any node that doesn't have a barrier or any node that is not out of bounds of the board. And we're going to look at all these neighbors. So if we've already seen a neighbor, if it's already in the explored set, don't look at it again. We're going to calculate this current temporary score. We're going to see, okay, what's the distance we've calculated so far to the node that we're looking at, plus the cost it would go if we move to the neighbor. So let's say we're at the start position, the distance from the start to itself is 0, plus the weight of going to a red square. So that would be 3. So our current score would be 3. Now, if the priority queue does not contain the neighbor that we're looking at, and we've already checked if it's in the explored set, so if we haven't done any calculations for it, we should on-queue it with its heuristic score as a metric. And I realize this is a bad variable name because as I'm looking down here, I said the heuristic score was that variable was h of x. This is actually f of x. So this is actually the sum, because if you see down here, this is where we populate heuristic score or update it with the distance plus the heuristic cost estimate. So we're actually using f of x as our priority. As mentioned before, this is just probably a bad variable name. So we're going to add that neighbor to the priority queue so that we could consider it to be explored. Otherwise, if it's already been on the priority queue, that means we've already updated its heuristic score. So if this temporary score, this temp of g of x, is worse, if it's greater than some other distance we've calculated to that neighbor, then we're going to skip it because this is a longer path than some other one we found in a different calculation of this node because we've already explored it. Otherwise, if the current score is better, so let's say, you know, we had a value of infinity, the current score is 3 is much better than infinity, then let's go and update this neighbor to say, okay, the parent of the neighbor is the start position, the distance from the start is our score, which in our imaginary example was 3, and then finally the heuristic score of the neighbor is the distance from the start, which was 3, plus the heuristic cost estimate, which could be all sorts of things, just the estimate from that second square to the finish. And we keep repeating that until we find the goal state. And so presumably, using this priority queue and using these estimates, we've explored fewer neighbors, fewer nodes in total to find the shortest path. All right, let's do one last demo as a hoorah for the series. Breadth first search, Dijkstra's algorithm, A-star algorithm, and then finally depth first search, which is just fun to watch it go. Anyway, guys, this is probably the last video in this series, but I'll definitely do more videos on the topic of pathfinding in the future. But definitely leave a comment if you have any suggestions for, you know, mini series you'd like me to do on other topics. Otherwise, I hope you have a happy day wherever you are, and I'll see you guys soon. Bye! But wait, there's more! If you want to check out other things I'm doing, I'm streaming on Twitch sometimes with games, piano. I've done some doodling and drawing before, so you can follow me on Twitch below. And then I also have my second channel where I unboxed my silver play button, which just came in the mail, which is pretty nuts. So thank you guys so much for helping this channel come so far. It's really insane. But I want to post more things to that second channel, things that might not fit with sort of the tight episodic content of this one, just some of my thoughts on things. So definitely check that out if you're interested in sort of the extra stuff that I like to do. Otherwise, for realsies, because you stayed all the way for this ending card and you're watching this cube sort of meander about in this sad depth-first search, I'm kind of committed to talking through this whole thing to watch it get to the end. So I'm just going to keep talking. Let's see, what was I thinking about earlier today? I just finished 1984, which was oh my god, it blew my mind. So yes, I did not read it in high school. I read a lot of great books in high school. I read a lot of great classics, but our curriculum happened to not read 1984. And I just read it. I just finished it a few days ago. And it was one of those where I was completely gripped by it because I felt like it was describing so much that I'm like so afraid of, I guess. And that's where with those types of dystopian books, you're always interested to see the end, right? Like, what point is it trying to make? In Game of Thrones, for example, everyone wants to know who's going to sit on the Iron Throne. Will the Iron Throne be destroyed? Will society be overrun by zombies or something? What's going to happen and who's going to win, right? Because that makes a point about what type of person or what type of values prevail in this world, and what does that say about our own? Like, I think that's why endings are always disappointing to people, because you expect it to have this kind of divine message that's above anything that you ever know, because the buildup feels so, magical, that you're expecting some big message at the end that's going to shock you and re-educate you. In any case, that's what I was kind of expecting with 1984. Like, hey, this is a huge classic. How is this all going to end? And to be honest, you always hear, the Hunger Games and all these dystopian movies were all inspired from 1984. And it's just like, I thought while reading it, all I knew before starting it was that there's a big political party, they're really creepy, Big Brother's watching you, and then it's about a guy living in that. And I was thinking, probably this is going to be where, the little guy becomes aware of the strange things that are happening and joins some organization, and they overthrow the big government. And so that's what I was expecting. I was expecting that's okay if it's tropey like that, because it supposedly invented a lot of the tropes we're using now. And I'm at least just interested to read it to see, hey, what it was the actual plot, where were these tropes actually based on? But I was so wrong, and it's so strange to me how movies, it really is like, I felt like I was conditioned to, and I don't think I'm one of the sheeple, but I totally am. I feel like I was conditioned to expect the moment when something would turn and something would turn out well. I don't want to spoil anything, even though it's been out for many decades. If you haven't read it, I think you really, really should. But I'll just say that it does not follow the tropes that you would expect whatsoever, to the point that I just felt like mind blown, empty, but also like full of vigor afterwards. It also just, I think the most meta amazing moment was when the main character receives this book that's supposedly from the Brotherhood that's rebelling against the government, right? And he reads through this whole thing, and you as the reader get to read its contents, and it says all of these things, like describing what the party's doing, what its true intentions are. And he says, I always knew this stuff truly, but we just reached our goal. I talked through the whole thing. Should I stop here? He says, I knew all the stuff that was contained in the book, but it was never laid out so systematically. And that's what I felt 1984 was. It's stuff that you already kind of know, but it's laid out very systematically, with very clear, elegant writing. And so now I'm just very skeptical of all of everything. I'll leave it at that. Maybe I'll post my second channel, like more of my, maybe I'll have like a little book club from time to time. Anyway, thanks for sticking with the poor depth first search cube. Hopefully you can truly see how long that took, you know, going in along for a few seconds with Dijkstras algorithm versus, you know, a full like monologue about George Orwell's 1984 with the depth first search. So hopefully that truly illustrates to you the how the different strategies do matter. But most importantly, for realsies this time, have a happy day wherever you are. If you're all the way here, if you've sat all the way through this, and I hope you have an extra super happy day because I'm willing to be biased. But I'll see you guys soon. Bye.